Hi guys, welcome to Learn Electronics Repair. This is a Apple of some sort. Yeah, you can see the Apple logo on it. All-in-one computer or whatever they call these things. I'm really not familiar with Apple. In fact, it's the first time I've tried to repair anything of theirs. This was brought into me by Handy Andy, together with a mobile phone. So Handy Andy says the phone he needs today, this was a couple of days ago, he brought it in with a replacement USB-C port for me to replace the broken one, and the replacement one was the wrong type, so I couldn't do it. He's taken it back. And this one, he says, before you switch this on, switch off everything else, because apparently it trips all the power out. Okay, so that's what we have. I'm not going to switch off everything else, but I am going to connect this to my light bulb. So let's do that. And I am going to make a light bulb video, guys. You've asked me many times, there's many others, but I'll make one. I will make a light bulb video. It'll be most illuminating, yeah? So anyway, let's get the camera set up so you can see what happens with the light bulb I have here. We'll plug this in and let's see what it does. Here it is. So we'll plug it in with the current limiter in the circuit. You can see it there. Okay, let's see what happens. Well, there's a short. Clearly there's a short, so that's why it was tripping everything out. Let's disconnect the power and let's see if we can figure out what the problem is. So this is the power supply. You can see there's a short circuit somewhere. There won't be any charge in the capacitor in here, the main high voltage capacitor. There's like a warning sign here, because as you can see, there was no voltage getting into here. All the voltage was being dropped by the light bulb. That's why the light bulb came on bright. So I don't really have to worry about high voltage in here, but I do have to trace the short. I think the first thing we'll do is actually remove the power supply from the main unit, and then we can take it from there. With the high voltage sign here, I don't know where the capacitor terminals are. They might be here. I mean, I will check this, because complacency is a very bad thing, or even understanding things can sometimes be bad if you only partially understand them and you think you understand them. I'll just have a quick look to see. So it looks like maybe these are where the capacitors are. Well, there's nothing there, there's nothing there, there's nothing here. I'm not sure exactly where they are. Two terminals here maybe, but I don't see any voltage around there, so that's a good thing. Okay, how do we get this out? Looks like we need some sort of star screwdriver thing. So it's fairly easy to get out. Oh, that's just typical. So is this typical of Apple? One screw is longer than the other one. We need to make a note of that or something. So effectively this is the longer one, this is the shorter one. I don't know whether that will be the same on the other end of it. Even shorter. You'd think for the screws holding the hard drive in, which is effectively user changeable, they make all these screws the same length. This is another one of the shorter ones, and this is the very short one. VS, yeah, I don't know if you can see what I'm writing on there, but I can see it okay. Take those off. And then we can get this. That's an even shorter again one. Another, same as that one this time. Okay. And this is coming out now. Just keep my fingers away from it a little bit. So there's a cable here that plugs into it. Hopefully, yeah, get that one out. What else do we have? This kind of like slides out a little bit, and there's something underneath it holding it in. Okay. I'm guessing the large capacitor is down here somewhere. Okay. I can see another cable here. It looks like it doesn't, yeah, it unplugs the other end. Well, the looks of it, that actually attaches here. This is probably like a little push the side of the clip in type thing. Yep, that came out quite easily. Okay, we're getting somewhere. There's still something holding this firmly in place. I can see where the large capacitors are now. That much I can see. They're not exactly where I thought they were. I'm still convinced there's no voltage in them. They come down this way. I'm pretty sure this is one of them. Nothing there. And this is the other one, possibly. Can't easily get to see. Okay, so this comes out. Right, we have it now. You can see the large capacitors are here now, okay? I'm convinced there's no voltage in them, but we will check. Nothing. Nothing. Okay, let's disconnect this. How does it actually attach? Well, it looks like it's soldered on here. And it goes off down to there. They made this thing a pain in the backside. Why? Why? There's definitely solder into the board there. I see another connector, if that's fair enough. That's the power coming out of this. Fiddly. Some sort of, no, yeah, there's a clip underneath, I think. Yeah, as a clip underneath it. And now we have this last one, which now we can definitely see is soldered on here and kind of disappears under there. You know, guys, I think the easy thing might just be to unsolder it and take all this apart to get to this socket, which is just the other side. Yeah. Well, you'd assume that was the easiest thing to unsolder if it wasn't for this thing stuck on the board. Ah. Does that just unscrew and come off or something? Yeah, you can see it's kind of like attached to this board. Okay, let's have a look. Looks like these are actually possibly terminals. Not sure. Okay, they're off. Huh. I think I see how it works. There's like little, yeah, little plasticky things. Well, so that's soldered there. But this one's soldered as well. No. This thing, guys, is a serious pain in the ass, but I'm going to have to unsolder it because I need to get to this board underneath it probably anyway. I'm going for a plan B and unsoldering this lot. I mean, this must come out one way or another because obviously this is designed to be removed by a technician and just replace the socket or the whole thing. But you would expect that to plug on there, really. How annoying. Okay, get in there. That's the black one, the grey one, and then the thin one, which is also black, but it's narrower. Okay, I have it out. I'll just clean these bits of solder before I forget. So here is our power supply. This is where the power comes in. So this comes in from this little PCB that sits across here, which came off quite easily once I got the power supply out. It was just the plastic clips, as I thought, and a bit of soldering. So this is your live and neutral coming in. Just go into continuity mode. Do we have a short? No. It reads open, okay? That's working. It reads open. So that sits here. Do you think the short's further back along here? Because there's no short on the input. So we can have a look. This is just like a little bit of a board, basically. So these are the two screws, which is probably ground, which goes to that terminal, the thin wire. These are your live and neutral. There's no short. That one goes to there. And that one goes to there. So that just feeds the power in. It does nothing else than that. Over-engineered? Probably. Let's have a look on the power socket. So this is the power coming in. Do we have a short? No. So there's no problem here. In fact, we can just check this now. So this will be live or neutral. That one, obviously not the other one. They're not shorted. The other one will be that one. Okay. And then the thin one will be ground, which, well, on the EU plug, yeah, probably not connected. Nothing. Okay, so this plug from Apple, I'm assuming, yeah, this is the original one. It's not a standard one. Okay, so thank you, Apple. This device is not grounded. Even though you went to the effort of putting all the ground wiring on the inside. Yeah, well done. Okay, so the short must be on our power supply. And here it is again. Let's have a look. So I can see this is where the power comes in. Here, this looks like a filter capacitor. Oh, there's the bridge rectifier. You see the four legs here? Bridge rectifier. These are the high voltage capacitors. This looks like a transformer here. Or possibly it's just an inductor, a filter. This is probably, this must be the switching transformer. So somewhere around here are going to be some large MOSFETs. We'll have to try and find them if we need to. But let's start with the bridge rectifier. So we know there's no short on the input. This sloping edge here is almost certainly the positive. Is there a short on the output? Yes. Let's check the bridge rectifier. So I'm going into diode mode, okay? To test a bridge rectifier is quite easy if you don't stick the meter probe into your finger, okay? These are damn sharp, they're supposed to be. So if we put the positive on either of the AC inputs, we should see a diode going to the positive terminal. And there it's a diode, okay? And if we put the black on the 2 AC, we should see a diode going to the negative terminal. Black to negative, red to positive. Makes sense, yeah? And we see a diode. And we see a diode. So that looks like the bridge rectifier is working, but we have a short on the output. But let's just check that, because when we put the black and see a diode to there, if we reverse it, they should be open. And we still see a diode junction. And the same here, with the black to the AC rather than the red, they should be open. And we see a diode junction. The reason for that, guys, is because there's a short circuit on the output. And let me prove that to you. You know, you perhaps wondered why that was there. I confess I lost a bit of the recording, had to redo it. Let's zoom down. So here is a bridge rectifier. And this has some markings. You can see plus at this end, it'll say minus at this end, a little bit faint, minus, and then the two in the middle of AC. Let's check it. So for a good one, as I just described, put the red lead on either of the AC and we'll see a diode junction to the positive. Okay? Okay. And if we put the negative on either of the AC, we'll see a diode junction to the negative. So if we put the black on, yeah, black, negative, synonymous almost. If we reverse it, it should read open. Okay, and it does read open. And from here, that conducts, black here, reads open. So that reads like a good bridge rectifier because it is a good bridge rectifier. But the other one doesn't mean it's bad because of how we're seeing diode junction both ways. It means there's a short on the output. We can read the short on the output anyway. Let's put a short on this one. Okay, and now it should read like the one in our circuit. So red to either the AC, diode junction, diode junction. Black to either the AC, diode junction, diode junction. Reverse it. So this should read open. We see a diode junction. And this should read open. We see a diode junction. So you can see that if we have a short circuit on the output of the bridge rectifier, we still see diode junctions between the legs, but they're in both directions where they shouldn't be. And obviously you do read a short on the output. So that tells us there's nothing wrong with our bridge rectifier, it's just got a short on the output. And we need to figure out now where the short is. Well, we're going to find the short anyway if we look across these capacitors. They might be in series. That reads short. That reads short. And short across the two, okay? So the most likely place for the short to be is in the switching transistors that drive this transformer. And it looks to me like they're under here. There's obviously some black gunk on because you don't want us to look. But that's where they are. How difficult did they make this? I can see what look like 4 screws there. Well, those are the 4 screws in the devices. So you can see the device. And just focus on it. Okay? I can see the device as a screw there, and that's what we can see here, I'm pretty sure. Yeah, this is like the tab. So it looks like the only thing that's holding this down, there's some plastic clips, but I don't think they attach to it. It looks like the only thing that's holding this down is the fact that it's soldered to the board. And it's soldered to the board underneath this horrible black stuff. Yeah, okay, I can see there's 2 legs there. Oh, maybe a leg there as well. I see 2 here. So those 2 are there. Oh, yeah, I can see them now. So that's the diode. This is a transistor. And this is another transistor. And there's something else there. Okay. How many devices on here? It looks like 1, 2, 3, 4. And I even know what they are now. Okay. 1, 2, 3, 4. Did any of you guys watch my other attempted repair on the ATX 800 watt power supply with a shorted bridge rectifier? If you did, and I'll link it from this one because I'm not going to go through it all exactly again. This power supply has PFC or power factor correction. This is a MOSFET. This is a diode, 2 legs, and here are 2 MOSFETs, okay? This one and the diode are part of the PFC, power factor correction, and these 2 are switching the transformer. You see how easy it becomes to recognise parts of these circuits when you've done it before or you've watched my video before. I know that's blowing my own trumpet, so to speak, but if you're watching my videos, I'm hoping you can see now how common this sort of thing is, and you know PFC, diode, MOSFET and 2 MOSFETs, and you'll also know that that one could go short, or one or both of these could go short and would show the short circuit on the output of the bridge rectifier. On the last one we had, there was no short on the output, but the rectifier was shorted, And the reason there was no short on the output is because all of this lot was powered through a low value power resistor, which had blown open circuit. Hence, there was no short anymore. Okay, so we figured out what we have. How are we going to get these off? We're going to have to unsolder it. There's no other way. Yes way, no way. I'll have to see if I can get this stuff off. How difficult have they made this? Well, it's like rubbery stuff, so it will come off. Okay. Rubbery stuff. We can see the 3 legs of the MOSFET now. We can see the diode. So there's going to be 2 more here. Get stuff off it. And the transistors are now showing enough leg to make them interesting, yeah? So, it's possible one or more of these devices are short, but it's going to take a bit of unsoldering to get this off. I think first, before we do that, let's see if we can figure out, A, is there a short here? And B, which one, possibly? So, the first thing to do is just continuity mode. My meter has a 40 ohms range. I'm now in the 40 ohms range, so I can now see down to 100th of an ohm. Let's have a look. So if these are a standard layout, that is the base or the gate. And these are drain source, and the same with this one, base or gate, collector emitter, okay, or drain source. If there's a short though, it's probably across these two. Well, we read a low resistance. That's closed. That reads like 22.57, but it doesn't mean the short's here if there is. It's reading low to the gate as well. Oh, that, maybe this is the gate. Let's have a look. If that's the gate on this side, then that reads like 25 ohms, and that's low. Yeah. What's our short read? The one across the bridge rectifier. Is it a 0? Yeah, it's a 0. So the 25 ohms isn't the short. That suggests this is the gate. Okay? And it's not looking good for that device. The diode, unlikely to read short. Well, that's not very helpful because that doesn't tell us which side of the diode is short, but it probably wouldn't help anyway. Yes, it would actually. I'll show you why. This could have told us something. In fact, it is telling us something actually. So, PFC circuit, you have your bridge rectifier plus minus, and in the PFC you have an inductor, quite a large one, a diode to the main smoothing capacitor, the bulk capacitor, the one that has the high voltage, yeah, 450 volts probably, something like that. And then from here we have the MOSFET, possibly a low value resistor, that drives the PFC. So this is your PFC. Okay. Ours, by the looks of it, is reading like about 20 ohms from the gate to here, which suggests it's gone. Unless there's something else we can see in the circuit that's reading that, but I can't think what it would be. I doubt it would have such a low value resistor here. On the output then, this effectively goes to your switch mode transformer that will have 1 or 2 MOSFETs in it. Looks like ours has 2 in actual fact, but the principle's the same. and this is your PWM, pulse width modulator. These two could be the same chip in actual fact. Okay, so if we have a short here, okay, if we have a short here, if this diode is okay, we will not see a short here. Because that diode, if it's okay, at the most, if you measure from this end, you would see a diode junction to ground. You wouldn't see a short. So from positive to negative, the red lead here, if that was short, you would see this diode junction. So in diode mode, you see about 0.6. It could be a Schottky diode, it could be like 0.15, but that's what you would see, okay, if that was okay and this was short. If this was short, then from here you would see 0, okay, you would have that. But from this side, it would read open because the diode stops you reading the short. So from here to here is not short. It looks like our diode reads short, and if I read from either side of the diode, I'm sure that's what we're going to see. So I think pretty much this tells us that that is short, and either this or this are short as well. Let's continue. So just in the ohms range still, we want to go across our diode, which we just did, and I believe it was reading short. Okay, that was reading short. If we go to the negative end of the bridge rectifier, which is here, so effectively this is hot ground, okay, let's have a look. So from the diode, short, okay, from this one here, well, one end will connect to ground anyway, that reads short. Yeah, probably one end is ground anyway. Is that component there blown as well? Need to look at that. And then on this side, I'm expecting to see the short as well. Well, actually, no, I don't see a short on this side. Okay. That's reading short. But these may be wired in series. Okay. Let's have a look. Well, the middle of this one goes to that end of that one. Is one end of this going to the positive of the bridge rectifier? Yes. But it reads short. One reads a bit more short than the other. Okay, we're going to have to take this lot out then. But it's looking like that diode is short, or we've got shorts both sides of the diode, but the diode's okay. Let's see how much fun this is going to be. I've just started the process and thought I'd better hit the record button. So what I'm doing with this first is using the hot air just to get some heat into this area. I'm not trying to desolder it with hot air, I just want to warm the whole area up so I can add flux, leaded solder more easily. So with some heat in there, I've just done the first ones, you can see. I'm not actually using flux at the moment, I'm just using the leaded solder, which obviously contains flux. Okay. This is the diode. This is why you need these BC3 tips, by the way. You need to get a lot of heat into this sort of thing to have any chance of doing it. Okay. Okay. So that's got some leaded solder on there. I'm going to heat that last one up a bit more. I'm not happy the way it took the solder. As I think quite a few of you guys know now, I'm waiting for a new handle for my vacuum desoldering tool. I really would definitely have used that on this job, but at the moment I'm using solder braid. Let's try it. Do I have any chance of this at all? You use a mixture of hot air, flux again, yeah. So warm it up. Nice and warm. Braid, and let's see what we can do with it. Okay, well, it's wicking. That's the good news, it is wicking. Yeah, I even have it pretty much clear. Okay. Looks like I actually got that one. Next one. Looks like I also got that one. Okay. This one might prove a bit more difficult, and I may have to come back in with hot air as well, just to get enough heat back into the job. Yeah, so it's not quite doing that one, okay? Could be on a heavier plate. I mean, it's almost got it, but there's no harm. Fresh solder. Fresh heat. Desoldering. Flux. Braid. That one is proving difficult. It's about the same as our first try. It may be desoldered. Okay, a bit further. Diode next. Okay, not perfect. Last two. Okay, guys, I don't think I've got them all. I will try to remove this, but I don't think it's going to come. Let's have a go without putting too much strain on it. Let's see if we've actually got any of the legs free. Okay. That one sounds like it came free. Hear the click? This one, no. These, no. No. So if I'm going to try and just rip that off now, I'm going to rip the pads and tracks off with it. There's another way, and we can try it. Okay, so what this involves is first of all putting fresh leaded solder on all of the pins, even the ones that look like they were desoldered. We've removed pretty much all the unleaded solder, so this is now just leaded. So we've actually soldered them back in with leaded solder. Okay. Clearly you can see why I needed the vacuum tool, really. And what we'll do is now we'll clamp this board. I mean, these capacitors are quite warm. It might be an idea to remove them first. I'm going to take a chance, especially if I can kind of like lift them up away from the board a bit. Let's have a quick look without causing any damage. Yeah, that one's pretty well free. Okay, if I can bend this upwards a little bit, there we go, yeah. That'll keep the heat out of it, yeah. Same with the other one. Okay. So I've lifted them away from the board. I could desolder them, but I think that's fine. What I'm going to do now is I'm going to get the hot air, put this into a vise, heat up from this side enough to melt this leaded solder. If I do it right, it won't melt the unleaded solder around these components, okay? I'll just melt the leaded solder, I'll be able to pull this off the board. Yeah, just be able to pull it off. Let's go on, let's have a go. So what I've done here is I've actually clamped the PCB in my bench vise between one of the transformers and the board. I've made sure there's no components here. It's not solidly, and I can take it out. You know, it's held tightly but not solid. It'll move a bit, but I just want it to stay in place basically. What I'm going to do now, and this is why I've lifted these capacitors away to stop too much heat getting into them, hopefully, I'm going to get a hold of the heatsink with a pair of long nose pliers. I'm going to heat up from this side with the gun. I'm going to take it off the board. If this doesn't work, it maybe damage the board. I'll have to find out. I've got the hot air in my left hand. I hope I've been losing a bit of weight. I'm not doing too bad for my age, I think. With a bit of luck, we'll melt the leaded solder before the unleaded melts on the other components. And this will come off. If our luck's out, something will go badly, horribly wrong. Okay. Nothing yet. Certainly takes a lot of heat. Don't want to get too close, but I want to melt the solder. I think it might be moving a little bit, so let's see. Not yet. Not yet, guys. Don't have to go too fast, take a bit of time. Just let the heat sink into it. This thing takes an incredible amount of heat. This is one of the worst I've ever seen to try and desolder. We may have to use a rather drastic plan C. Well, that failed quite spectacularly. I managed to melt one of the little plastic things there, but that's not in itself a big issue. It just snapped off now. The reason it failed, I can see now, is that these two pins are actually attached into the heatsink itself, and they would have to be desoldered. I didn't have any leaded solder to these, so they weren't going to. But to get those two unsoldered, you're literally going to have to get enough heat in to get the whole heatsink up to the point where you'll melt the solder, and that ain't going to be easy, guys. You can even just try to get some leaded solder on them without melting any more plastic standoffs. Let's have a go. Well, I can get it on. I mean, I can get the leaded solder on there. This one. Yeah. Try wicking that off. Okay. Okay, I don't think even the vacuum desoldering tool will help with this particularly. I would have to say when they built this, they really didn't want anybody to take it apart. Okay. I could have another go. I mean, now I've done that, I could try it once more. You can see I've actually managed to unsolder these two and this one. I haven't tried these ones again. Can't even get this thing to come loose. If I get the heatsink to come loose, it'll be a good sign. Have a go. I've just got my long nose pliers wedged in behind it. Yeah, I mean, it's bending up a little bit. That's a bit of a sign. There's a third pin, and there's only the two. Okay, let's carry on. Let's not be defeated by this, okay? If we can avoid it. Okay. Add some more leaded solder to this, get some more heat into these. See if they'll pull out of the board. All I'm doing, of course, is just bending the legs here as I do it. But we can live with that. Yeah, that's going. Did you hear it creak? If I get these out, I'll probably be able to do it the way I was just trying with the vice and the hot air. Okay. Worst comes to worst, the guy just needs a new power supply. It might end up the case anyway. So nothing much to lose here. Okay. That's going. Try this one again. I could just cut all the legs off the devices and replace them. They're quite probably shorted anyway. You know, there's ways and means, guys. There's ways and means. But I think the way I'm doing this at the moment is getting us somewhere. Creak. That one sounds like it's gone. That's going. Once more. So that seems to be pulling in there. This one again. Yeah, so I'm now with a bit of brute force actually getting somewhere, guys. Whether there's a better way, I really don't know. That one's gone. This one is, I think it's just, I think it's gone. Yeah, I think that's pretty much gone. Okay. Yeah, they've come out now. So let's again go with the technique of with the vice and let's see if I can get this out this time. I'll add fresh leaded solder again. And maybe this time we'll have it. Let's give this another go then, guys. Now I've got the heatsink away from the PCB. It is just the component legs. If I knock the camera over with the hot air, by the way, that'll just be funny. So let's melt the solder now, the leaded solder, and see if we can get us off the board. I'll keep away from these plastic things this time. Still doesn't want to come easily. Yeah, it's coming. I think it's coming, guys. Yeah, it's coming now. Yeah. And there we have it. Okay. Let that one cool down. And here we have it. You can see the PCB has survived that very well. There's no damage to it. There is what looks like a thermistor which goes here. That's it. It was underneath the heatsink. It desoldered by itself, fell on the floor, but I have it. So we can put that back. I'll just put that somewhere safe for now. And then we have the output devices. So we can now see what we have. This one is the MOSFET for the PFC. You can see it is a 6R199P. Yeah. Or this HEQ 243. I think that's the part number 6R199P. This is the diode in the PFC, so BYV29X 600 volt probably. And then we have a pair of MOSFETs, they look like, which drive the output stage. Let's get the components analyzer. Okay. Let's see what we've got. So MOSFET first. Is this short? No, it's a MOSFET. Okay, so that reads okay. So the other one's probably okay as well. Normally if one goes, they both go. Yeah, let's try it. MOSFET. Okay. So this is the diode that was reading short. We can see a short here. I do need to put a battery in this. No, it's a diode. It's okay. And then we have the PFC MOSFET. So if this reads okay as well, then we've got to look on the circuit board to find out where the short is. Okay. Short. Ah, okay. So that one is short. So we do have a shorted MOSFET. The fact these are mounted upside down to the way I thought they were tells me effectively when I was looking at them in the circuit that this is the gate and not this one. That's why I thought the gate reading was very strange. So there's our short. What's interesting is I can see a short circuit both sides of this diode. Let's have a look. Is there something else short on this? Well, we'll start with the bridge rectifier. And the short is now gone. I'm reading this with effectively the black to this end, the positive end, so it will read like a kind of a double diode junction. This way it should read open. Yeah, climbing up, capacitors were charging. So we can have a look here. It's okay. It's okay. And let's look for shorts on the output end. So this is where the diode went. There's now no short. That's ground anyway, I would say. Yeah, being like MOSFETs, and we know they kind of back to front, I think we'll find that from the positive of the bridge rectifier goes to one of these. That one, okay. But not this one. Okay. That goes to there. These will probably connect together. Yeah. And then this one will go to ground. So that reads okay. That's what we'd expect. I'll just explain what I was checking for there with the two MOSFETs, or rather where they fit into the circuit. So normally with an ATX power supply, and this is a similar design to be quite honest, although it looks rather different, it's basically the same sort of thing. They usually have two transistors or two MOSFETs driving the output, the transformer, the main transformer. And although there are many other ways to design switch mode power supplies, the ones that you find with two transistors and often two capacitors, two large electrolytic capacitors, fall into three types really. So these are the most common ones you're likely to find. This first one uses two MOSFETs. This is your plus and minus, so this is your large capacitor. Usually this just has one or several of them in parallel, not series, okay. Plus minus from the bridge rectifier. And then you have an inductor coil. This is not the transformer, okay. You have an inductor coil, then you have the transformer coil, primary. So this is your secondaries on here. And then you have a high voltage capacitor. coming back to minus. So you get that type, okay? This is called an LLC circuit, which stands for inductor, inductor, capacitor, inductor, inductor, capacitor. And it's a form of resonance circuit. It's also called a resonant tank circuit, yeah? So you have two MOSFETs that are switching this end of the coil, and this forms some sort of resonance circuit. As it says, I don't know the exact in and out. I just know how it connects together and basically how it works. So you find that type. Then you find the type that has two large capacitors on here. So this is another common one. You will have two large capacitors. And they're quite easy to identify these because of the way they are, yeah. Two large electrolytic capacitors. You may wonder why you see these two at 200 volts each. Is it because you couldn't put one 400 volt? No, that's not the reason why. Positive and negative supply. And then this one, basically you have two MOSFETs. Okay, that's going to ground. And from the junction of the two MOSFETs, you have a coil, your transformer winding, and that comes back to the junction of the two capacitors, yeah? So, again, the MOSFETs switch on and off rapidly, switching this end of the coil, the other end of the coil goes to here. This is called a half bridge. Okay? And that's another type you will find. And all these designs have advantages. Sometimes you'll find over a certain amount of wattage required, you have a particular type. Some, you know, are more capable of making high wattage power supplies more efficiently. So we have that one, and we have another one which is really common. So I'll just draw that as well. And it's a variant of this, really. Again, this one has two large capacitors. Okay. We have the two MOSFETs again in series. So this is your plus and minus again, your high voltage, okay? And then with this one, we go from here and we have a capacitor and the coil to here. So on both of these, this is the primary of your transformer and the secondaries are here, yeah? And the same with this one. This is kind of like a cross between the two, if you like, and this is called an LLC half bridge. There you go. So that's the three that you're most likely to find. If the circuit has PFC, regardless of which one it is, we'll draw those on this one. The PFC, as I drew before, you have the diode here. You have the other inductor here. You have another MOSFET here. You go to ground. Okay? And obviously your controller to pulse this. What I was checking then, and if you look at all three of these designs, in every case, the two MOSFETs are in series connected from the plus to the minus, or if you like, positive and hot ground. Okay? And I was checking where those MOSFETs were fitted. I could see from one I had a connection to here. I had, for example, like drain, source, drain, source. I could see a drain connected to here. I could see a source of one and a drain of the other one connected together. And then the source of the other one was the one that made like a short to ground. And it should go to ground. You can see on each of these circuits that one of the sources will go to ground, no matter which one, okay? So that's what I was checking for. And I found that. So I know that circuit's okay and there's no shorts across it. So I know there's no short here to here, okay, on the board. And the device is really okay. What this does not adequately explain is why originally I saw a short here to ground and I saw a short here to ground. And this diode read short, yeah? This device was short, so I obviously had a short on this end of the diode. But if you look, there's no path, or there shouldn't be any path, to read a short from here to here. If this is connected here, there's still no direct way. If the MOSFETs are short, fine. If that capacitor was short, but then it would only read to that one. So it doesn't explain why I could read a short across this diode. I want to have a look at that next. Just before we do, let's see which of these three we actually have. Yeah. Well, we can see there are two large capacitors here. And we know there's a pair of MOSFETs, and we also know they're connected in series. So basically, one end of the MOSFET goes to ground or power. Ground, in fact, it's the negative end of here. We have two connecting together, source and drain. The other end goes to the positive, we can see that. And we have what looks like a large capacitor here, and it looks like an inductor as well. And this is the transformer coil, the primary. So the first thing we really need to check is whether these two capacitors are actually in series. So this is a half bridge or something similar to that, or whether they are in parallel, just one capacitor, and this is an LLC type circuit. So that's easy. Two positive ends of the capacitors connect together. The two negative ends connect together. So these are in parallel, not in series. That means this is an LLC type circuit. And in fact, we can see the component parts really. If we have a look from the other side, this is the junction of the two MOSFETs that connect together, okay? And that goes, if we look, this is where our capacitor is. So one end is here, the other end is here, and this is the inductor, okay? And this is the main transformer. So I can check from the junction of these two, and I should have a connection to the inductor. There, this is the transformer winding. This is the other side of the inductor. This is the capacitor. And then from the other side of the capacitor, I should have a connection to ground. Let's have a look. This is where the capacitor legs are. Yeah, there. Okay. So I have a connection to there. That's ground. If I just look on the other side, yeah, you can see that is actually the end of the capacitor negative. So we definitely have an LLC circuit. This capacitor then, we can just look at the markings on this. So this should be a high voltage capacitor in the tens or hundreds of nanofarads. Yeah, you can see this says 333J. The J is tolerance, I believe. The 333 is 33 and 3 zeros, which is 33 nanofarads. Then we can see 1000, which will be the voltage rating. So it's fairly easy to figure out the topology you have. Just look for the extra inductor in series with the transformer winding, the large high voltage capacitor, and check whether the main capacitors, main smoothing capacitors, if there are two of them, if they're in series or parallel. I have seen higher powered ATX power supplies with 3 of these in parallel. It's possible there could be even more on very high powered ones. And this capacitor on an ATX power supply is usually a reddish brown colour. I'll just show you one actually. Here's one I've been stripping for parts in actual fact. And you can see the same, the two large capacitors, the two switching transistors, and that's the brownie coloured one I was discussing. So again, this is another one of these half bridge LLC circuits. So now you know how to identify a lot of the common topologies of these power supplies. You should have a better idea of how to diagnose them, what to look for, what to expect on your meter. There are other topologies that you may find, but particularly on ATX power supplies, there's one other I have seen. You're only likely to find this on high powered ones over 1000 watt, but this is what's called a full bridge. So with a full bridge, you have 4 MOSFETs driving the transformer. Okay, 2 here, 2 here. Again, with obviously the gates and the controllers, and the coil, the transformer primary is there. Okay, and these switch in pairs. So this is your plus, your hot ground or minus. So effectively that one switches on and this one switches on, which pulls through that way. And then in the other half of the cycle, this one and this one switch on, which pulls current back through that way. So the current is alternating, being driven from both sides. Because the coil is being driven from both sides rather than one end being held fair, basically at a fixed voltage between the two capacitors, this is more efficient again. And you will find this in very high powered ATX power supplies, so I thought I would just mention it for completeness really. Although this isn't complete because there are other topologies such as push-pull. If you're interested, you can just go and look for this, SMPS topology, and you will find others. Now I've removed the components, this is going to be much easier to clean the solder out, and fitting this back in will be much simpler than it was removing it. Again, we can clean these holes easily. So actually putting this back on is not going to be a problem, anything like removing it was. We will now find that solder braid will do the job just fine. If we get a bit of heat in, again, but just a bit gently warm it a little bit. Okay, let's try to clean the holes on the PCB. Best way, once again, a bit of leaded solder. Start with this one, leaded solder, leaded solder. Bit of flux will help the braid to wick this up, and this should come nice and clean now. Yeah, and that you can see is clean. One thing I will say for this PCB, although it sinks a hell of a lot of heat, it can also withstand a lot of working with the soldering iron. The tracks don't come off easily. Yeah, you see how easy it is now, guys. Once the components are out, it comes off much easier. Get a bit of leaded solder. Both pins. And it's clean. Putting a bit of smoke away from me. Again, with these I might have to add some leaded solder first. That one came clean anyway. So did that one. So did that one. So really, it's just the legs of the component that cause the problem when you try to get the solder out of the hole. Okay. Last one. I say last one, there is one more, and that's where the heatsink was attached. It really caused all the problem. This one's come clean anyway, and I'm sure this one will clean. There. I hope you think that's almost a professional job, yeah? It's good enough for me. Okay, the PCB is nice and clean now. I just used the solder braid and extracted the solder from all the holes. It's very easy once the components are no longer in. We have the two holes where the metal studs go from here. So this will be actually easy to fit back in. We just need to order one of these. So here is the PCB. Everything would suggest we still have a short here where the diode was. We do have a short there where the diode was. And that's not right. I mean, we've just seen the circuit. So how have we got a short there? Looks like one end goes to this capacitor. But there's no short to the other end. One end of this will be power anyway. The power coming in from the main capacitors, one of them, which probably goes to quite a lot of places. Oh, there seems to be a short there. We need to have a look, see what that is. and there also. So we need to have a look around here. We really need to see where this track's going to try and figure this out and see what these devices are. Let's get it under the microscope. Well, these devices say LT4B14 on them. There's one of them connected across these low value resistors, but I'm sure these will be current sensing resistors. You'd expect this to read low. That reads 0.2. 0.2. Let me try the milliohm meter. I want to see if these are connected to each other, and I need to use a lower resistance meter. Okay. The screen isn't cracked, by the way. It's just a reflection of something. Yeah, off the roof ceiling. Let's have a look. So, I'm not sure how long the light will stay on. This is the resistors, which are the current sensors. So they're reading 0.043. What's this reading? The same. So that probably is connected across there. And what about this one? 0.135. And what about across the diode? 0.341. So that's different. I need to have a look to see what these devices are. It's quite possible that that one is connected across these resistors, in which case it would read extremely low. Let's have a look. Sorry, it's a bit awkward for me to get, but yeah, that appears like it does go to there, and here appears like it does go to there. So that seems to be connected across those. Okay, this one, I'm not totally sure, but it does read short. There's a few more power devices around here. I'd imagine that whatever's short is going to be something fairly hefty. That reads okay, that reads okay. Let's see if we can find out what these things actually are. So LT4B14. Let's try the other number on here. There's another number on them, S8JC. Let's see if that finds anything. And yes, it does. So S8JC has actually found this, and it is a surface mount rectifier. So that most certainly should not read short circuit. Okay. Our one is a 600 volt. It's that one. 420 volts RMS. 8 amp. Okay. So that shouldn't be reading short, that's for sure. The one that's connected across these resistors, and I think now we can actually see that it is connected across the resistors, it's quite probably okay, but I guess I need to remove it anyway just to prove it. This one, well, it comes from sort of a terminal there. It comes from the direction of this diode for sure. Okay? And then that goes off into this is probably the hot ground or something. So, or even where the mains comes in. So let's remove these two. This one I suspect is actually faulty, and this one may be okay, but the only way to prove it is either to remove these two resistors or to remove the diode. We may as well remove the diode. Here are the diodes. Let's have a look. Well, that one reads short, okay. I'll put the meter on the diode mode actually. But it's definitely short, regardless. And the other one actually reads like a diode. That's the one that was across those low value resistors. Let's have a look at the board now. Let's see if we still have a short. Here is the PCB. This is where I unsoldered the two diodes. Came off nice and cleanly. Didn't dislodge anything else. I used the method I've used on many videos with this sort of thing. So I apply leaded solder to each end, leaded solder and flux, and then I heat up the whole thing with the hot air gun, and they come off. And the leaded solder will melt, or basically, if you like, the alloy of leaded and lead-free solder on here will melt before the lead-free solder and anything else. And you can see, came off cleanly. No Kapton tape required. In fact, Kapton tape is just going to make this more difficult for you because you can't get heat into the PCB properly. Okay. So this is where our diode was. Do we have a short now? No, we do not have a short anymore, okay? Probably won't read anything, maybe read a diode in one direction. No, it doesn't, okay? So, we've definitely got rid of the short on the board now, and we know what components we need at least to put this back together, and then connect it with a light bulb in series, give it some sort of current limiting, and see if it works. I think I will order the chip as well, the one that actually drives the PFC controller. This one, I think it's worth changing that as well. And I'll get like more than one of the diodes, and I will get obviously more than one of the short circuit MOSFET. Let's have a look to see how much it's going to cost in parts if I can't get them locally. These then are the parts we need to actually complete the repair. These are the short circuit diode, the short circuit MOSFET. This is the diode on the heatsink which isn't faulty, and this is the controller for the PFC, which I don't know if it's faulty or not. But to be quite honest, this might have been stressed quite a lot by the other fault, although the MOSFET is on effectively not drawing any current through this. When it goes short, it's on the other side of the circuit, so maybe not. But to be honest, if I can get those as well at a reasonable price, and I will order these anyway because I don't know what condition that chip is in, and it may have been damaged when this failed because it's driven from this, then I think we have a very good chance of repairing this. Let's have a look to see how much these parts will cost and whether we can get them. I can get all of the parts I require then in smallish quantities, but I won't buy just one. A, in case something else goes wrong, I have to replace them again, and B, because if I ever find something faulty like this on one device, I will order a few, because to be honest, I'll probably find it faulty again on something else. So this is the chip, the PFC controller, which may or may not be faulty. These are the BYV29X. That probably isn't. I mean, it tests okay, but they're not expensive. For $5, I think I'll just get some anyway, for the hell of it. Yeah. This is the 6R199P, the MOSFET. $5 again, not expensive. Oh, I picked the wrong package, but it's the same price actually. So I need to make sure I get the right package. And then these are the LT4B16, sorry, SHJC, 10 of them, again, not expensive. So adding all that up together is €17.84. I'm the Canary Islands, so immediately I can remove the EU VAT or Spanish VAT. So divided by 1.21. That'll cost me a bit under €15, €14.70. I will add that to the repair cost for this device, but I don't think that's out of the way, and I will have a nice handful of spares for other jobs. I really don't think the customer is going to be complaining if I'm charging him that sort of price for parts plus the labour to fix it. So I hope you enjoyed that one, guys. I think we looked at some different approaches to fault finding now. This is something I've been wanting to do for a while, but it depends. I don't know when I open these things up what I'm going to find, if I can fix it, if I can even diagnose what's wrong with it. This one's looking quite promising, but I will have to order parts. I doubt very much I will get these parts in the capital Las Palmas, even the 2 parts I actually need. I will try. Otherwise, it's AliExpress. I'll probably save a little bit more on that total as well with combined shipping. But I think the thing that you will really take away from this video and learn is that if you understand the topology of the device, which is why I've now told you the topology of these type of power supplies and ATX and how to recognize which one you have. If you understand that, then it's very easy when you're reading something like a short on your meter to know that you shouldn't see a short there. It's not just part of the circuit, like for example on those very low value current sensing resistors with the diode across. I did say this diode is almost certainly okay, and it was. And the other one, I could say definitely, because the way the circuit topology is, there should not have been a short circuit there. And I really hope you saw that, and if you didn't know it before, I hope you've learned something, yeah? Because that's what this channel's about, and I really enjoy teaching you these things and showing you these things. So on that note, I hope you'll be back soon. Hope to see you all soon on another Worthy Electronics repair video. Ciao for now, guys.